is the first video in a series covering high school level C mathematics. This video, though not particularly heavy on mathematical calculations, is meant to introduce the notion of numbers as a set and how we write intervals. And then I want to try to explain, in a historical context, why we use the base 10 decimal numerical system that we use, that is the numbers 0 through 9, as opposed to any other numerical system. Like, for example, the binary system, base 2 binary system consisting of zeros and ones, which we do use, but is primarily used for computers and electronics. So without further ado, let's get started. Numbers were first invented as a way of counting. Take yourself back thousands of years back to when human beings were hunters and gatherers. And picture this hunter right here. He has caught himself 3 fish, and they would indicate this using their body parts. So pointing to the fish and holding up 3 fingers. They would also use pebbles. So a stack of 3 pebbles would account for the 3 fish, or they would make carvings into a wooden rod. Now, 2 interesting facts about these ways of counting. The carving rod here has actually been used all the way up until the 18th century. And the Latin word for pebble is the word calculus, which you may have heard before. Calculus is a significant branch of mathematics, and the word is just the Latin word for pebble. Now, with these simple numbers, I want to introduce our first set of numbers today, which are the natural numbers. And the way to describe this set, I will show visually by drawing a circle and then putting all the elements within the boundaries of this circle. Here we have the number 1, 2, 3. We also have 35 and 892, and so on. We describe this set using a capital N. And it's also customary to use a particular typeface for this letter, which I'm going to indicate by an extra line right here. We can also describe this set of numbers mathematically. And the way we would do that is we would write n equals, and then in between curly brackets, we'd list all of the elements of this set. 1, 2, 3, ... to indicate that this goes on all the way up to infinity. So here we have a mathematical description of the elements within the set of natural numbers. Going back to our history, well, eventually civilization came around. With the invention of agriculture, people no longer had to move around and could settle in one place. This led to the formation of cities and civilizations. And no doubt they would need more than just their body parts to account for everything. So different ancient civilizations developed their own numerals. Here I've listed a couple of different ancient numerals. We have the Hebrew, the Egyptian, the Greek, and the Roman numerals. If you're from the Western world, you have likely seen the Roman numerals before, and that's because they are still used, though not for doing mathematics. I've also included some higher value symbols here, and in fact there are many more. Now you may be thinking, why use these higher value systems? Why not just use the numbers 1 through 10 in a similar fashion like we do? One might conceive of the number 53 as being written in Roman numerals by writing a 5 followed by a 3. But this would actually be wrong. This is in fact the number 8. And that's because these ancient numerals are to be considered as an advanced tally mark system. I'm sure you're familiar with these basic tally marks here. Like this would represent the number 8. And what you have to do is you have to add the value of all the symbols together to get the number. Let's take an example using Roman numerals. Here I've written the number 2856. And in Roman numerals, this is 2 M's, each representing 1,000, a D representing 500, 3 C's, each representing 100, an L for 50, a V for 5, and an I for 1. That adds together to 2856. And as you can tell, this is actually a rather cumbersome way of writing large numbers. And so the solution to this would be the invention of a positional system similar to the one that we use today. But before we go into that, I want to talk to you about negative numbers. Negative numbers likely emerged with trade. We can picture a situation down here where the farmer has made a deal with the shepherd to trade his wife for 4 sheep. Seeing as the shepherd only had 3 sheep to begin with, that means that he is now 1 sheep in debt to the farmer. So we say he has minus 1 sheep, and for the time being, no sheep to herd. Even to this day, we actually use negative numbers to account for debt. You can imagine going to the bank only to find that your bank account has a balance of minus $100. And in that case, you know you have some catching up to do. These negative numbers we include in our next set, which is called the integers. In here we have the number minus 1, minus 2, minus 48, and minus 302. And many more, of course. We also include in this set the number 0. A note on the number 0. The number 0 didn't come along until much later in history compared to where we are right now in our story. Imagine the hunter going out one day only to return home having caught nothing. Or the shepherd going to bed at night and waking up in the morning finding that, to his delight, the wolf hadn't taken any of his sheep. In both these cases, they were unlikely to think of themselves as having caught some 0 amount or having lost some 0 amount of sheep. But that is in fact exactly what 0 is, a quantity of nothing. We denote this set using a capital C. And we can also describe this set in a mathematical notation. Next, let's talk about fractions, or what we would call the rational numbers. Imagine you have a loaf of bread that you need to split evenly among 3 people. In this case, each person gets 1/3 of the whole. In fact, the ancient Egyptians also had symbols for a particular type of fractions. This would be the symbol for 1/3, and this would be the symbol for 1/5. These fractions here are called unit fractions because they have a 1 in the numerator. But the Egyptians didn't have a symbol for a fraction like 7/8. Today we use fractions with integers in both the numerator and denominator. So here we have our set of rational numbers. The rational numbers also includes all the integers because any integer can easily be written as a fraction. Take the number -2 and divide it by 1. You have a fraction -2 divided by 1, and that is equals to -2. We denote this set by capital Q. The set notation is a little more technical in this case, and it reads: the rational numbers are all the numbers for which the number can be written as a fraction p divided by q. P belongs to the integers, and q belongs to the integers, and q cannot be 0, because we can't divide by 0. Let me show these fractions on a number line. Perhaps you've seen a number line before, maybe in a coordinate system. Typically, a coordinate system has an x-axis and a y-axis, and it is just that, 2 number lines. This number line here goes all the way from -infinity to +infinity. But I want to focus in on the numbers in between 0 and 1. Here we can put the fractions we've talked about so far. 7/8. But we can continue. 1/6 is here. 1/12 is here, 1/24 is here, and in fact we can fit an infinite amount of fractions in between these two numbers. So now we must have all our numbers, right? If we can fit an infinite amount of numbers in between any numbers on a number line, then we must have all of them. Well, that's not quite true. There's actually still some numbers that we need, and these are the irrational numbers, numbers that cannot be written as a fraction. But before we move on to that, I want to talk briefly about intervals. Intervals can be used to describe a set of numbers in between two numbers on a number line. And they have a couple of different properties that I've listed here. An interval can be closed, and if we look on a number line here, it is shown by drawing two filled circles at each endpoints of the interval. Using intervals, we can use square brackets to indicate that these numbers are contained in the interval around -3 to 4. And we can also use our set notation. X belongs to the real numbers, we'll get to that soon, for which x is larger than or equal to -3 and less than or equal to 4. An interval can also be open, in which case you'd use these unfilled circles at the endpoints. The square brackets will be facing away, and x is now strictly larger than -3 and strictly smaller than 4. The next one here is half open, and I've left some information out here for yourself to figure out. So think about it for a little bit. We have an open circle here at -3 and a closed circle at 4. How would the square bracket face in this case, and which inequality symbols are we going to have in between the numbers and x here? Finally, an interval can be unbounded, which is the case here. These are all the numbers going from -infinity to 4. You could also say that it's an unbounded interval, but you could also say that this interval is right bounded, which is to say it is unbounded to the left. It has all the numbers going to the left of 4. In our set notation here, x is simply just smaller than or equal to 4 in this set. And here I want to note also that the square bracket is always facing away from the infinity symbol, because we cannot include infinity in any interval. So, have you figured out this one yet? This one has to be open, and this one has to be closed like this. And then x has to be strictly larger than 3 and strictly smaller, not strictly, but less than or equal to 4. Now there's one thing we haven't talked about here, and that is this symbol here, the R, which stands for the real numbers. This is an expansion of the numbers that we already have to include the irrational numbers, numbers that cannot be written as a fraction. To show the existence of these numbers, an ancient Greek mathematician named Euclid was looking at a square with the area of 2. The size of the square must be square root 2. And he managed to prove that the square root of 2, which is a number roughly 1.41 and then some more decimals, cannot be written as a fraction. Therefore, we have this next set of numbers, which is called the real numbers. I've listed some more numbers in the diagram here, which one of them I'm sure you are familiar with, which is the number pi. There's also Euler's number here, which we will get to in a later lesson. And there's also square root 3 and many, many more. When it comes to the set notation for this set, there isn't really any. So I've just written R is equal to the real numbers. You could also consider the set of real numbers as any number that can be written as a decimal. So here we have it. These are all the numbers that we'll be working with, but I do want to finish the story that we began. These last two sets of numbers are a little bit more complicated and would have been difficult, if not impossible, to describe using Roman numerals. And as I said earlier, the solution to this was to invent a positional system. The system that we use today is a base 10 decimal positional system, which was invented by Indian mathematicians and popularized by Arabic mathematicians, which is why it is called today the Hindu-Arabic numerical system. Which are the numbers 0 through 9. It's a positional system where we reuse the symbols and assign them different values according to their position in a sequence of numbers. So if we take, for example, the number 742, and if we read this from the right to left, then we have 2 ones, 4 tens, and 7 hundreds. We could write this in this way. This here number, 10 raised to the power of 0, is actually just equal to 1. Any number raised to the power of 0 is equal to 1. At the time, different civilizations developed their own positional systems independently of each other. The Mayans used a base 20 numerical system, and they wrote their numbers vertically. So for example, the number reads from the bottom up, 9 ones. Again, I'm going to write a 1 as 20 to the 0th power here, plus 120, plus 1 400. This is equal to 9 plus 20 plus 400. 429. There are also other numerical systems, for example, the binary system, which is used for computers and electronics. This is to do with the inner workings of these electronics. A binary system is a base 2 system. It has 2 symbols, 0 and 1. And to show you an example, one 0 1 1 0 1 is equal to 1 times 2 to the 0th power plus 0 times 2 to the 1st power plus 1 times 2 to the 2nd power plus 1 times 2 to the 3rd power and plus 0 times 2 to the 4th power plus 1 times 2 to the 5th power. And notice here how the numbers here are represented here, here, here. And if you add all these numbers up, you get the number 45. So there's a number of different numerical systems with different bases, one base 20, base 2, and base 10. In fact, we could use any base for our numerical system. So why do you think it is exactly the base 10 system that we end up using? Well, the explanation is most likely because we have 10 fingers that we use to count on. The Mayans have a base 20 system because they would also count using their toes. And in fact, any system can be used. Alright, so this is the end of the video. Thank you very much for watching. In the next video, I want to talk about arithmetic. I want to introduce basic mathematical operations for our sets of numbers here, like plus, minus, division, and multiplication, and also talk about the order of these operations. Thank you very much for watching.